Right now, as you listen to this, something is hiding almost directly behind the Sun. Tomorrow, October 21st, 2025, 3I-ATLAS will reach solar conjunction, positioning itself exactly on the opposite side of our star from Earth. For over a week after that, we cannot see it, we cannot track it, and according to Harvard astrophysicist Avi Loeb, this timing might not be coincidental at all. Because 9 days from now, on October 29th, this 5-kilometre wide object will reach Perihelion, the closest point to the Sun, receiving 33 gigawatts of power onto its surface. The same moment astronauts use for gravity assist manoeuvres. The same moment a spacecraft would fire its engines for maximum efficiency, and we will not be watching. On October 13th, just 7 days ago, researcher David Sereda reported something that should not be possible. Light pulses, not random fluctuations, not natural brightness variations. A pattern, 5 flashes, then 8, then 13. The Fibonacci sequence broadcast from an object travelling at 200,000 kilometers per hour through our solar system. The same day, 108 years to the date, that 70,000 witnesses in Fatima, Portugal reported seeing the sun dance in the sky. NASA's Solar Dynamics Observatory went offline. The HIRISA imaging system that was supposed to capture the highest resolution images ever taken of 3I-ATLAS during its Mars flyby, those images are still being withheld, and in 65 days on Christmas morning, this object will reach a geometric alignment with Earth that matches the angle of the Great Pyramid of Giza. You're not hearing speculation. You're hearing documented measurements, verified trajectories, and timing so precise that the probability of coincidence has been calculated at less than 1%. 8 anomalies, 8 violations of everything we thought we knew about interstellar objects. And today, right now, while 3I-ATLAS moves toward its hiding place behind our Sun, we are going to walk through each one. Before we go further, if this is already sending chills down your spine, do me a favour and hit that like button and subscribe to the channel. Tell me in the comments where you are listening from, what time it is there, and honestly, do you think we are being visited right now? And if you want to help our community grow, share this on X, Facebook, Reddit, or send it to someone who needs to hear this. Thank you for always supporting our community. The Fibonacci message, October 13th, 2025. 8 days ago, on October 13th, David Sereda was monitoring 3I-ATLAS through multiple observation channels when he detected what he describes as structured light emissions. Not the gradual brightening and dimming you would expect from a rotating comet. Not the chaotic fluctuations of outgassing. A sequence. 5 pulses of increased luminosity, then 8, then 13. The pattern repeated. Sereda, who has worked with MIT physicist Bogdan Maglich on nuclear fusion research, immediately recognized what he was seeing. The Fibonacci sequence. 1, 2, 3, 5, 8, 13, 21, 34, 55. Each number the sum of the two before it, a mathematical pattern that appears throughout nature, from the spiral of nautilus shells to the arrangement of sunflower seeds, to the structure of galaxies themselves. The pattern that generates the golden ratio, phi 1.618, the proportion that seems to be woven into the fabric of reality itself. Now, here is where this gets strange in a way that makes your skin prickle. October 13th, 2025 marks exactly 108 years since the miracle of the sun at Fatima, Portugal. On October 13th, 1917, an estimated 70,000 people gathered in a field after 3 shepherd children claimed that the Virgin Mary had told them a miracle would occur on that specific date. Witnesses, including skeptics and journalists, reported seeing the sun appear to dance, spin and plunge toward Earth before returning to its normal position. The event lasted approximately 10 minutes. Secular newspapers covered it. Photographs exist of the crowd staring at the sky, many on their knees. Whatever happened that day, something was witnessed by tens of thousands of people simultaneously. 108 years later, to the day, Sereda reports detecting these Fibonacci pulses from 3I-ATLAS, and 108 is not a random number. It is a frequency octave of 432, a number that appears repeatedly in esoteric traditions, in the dimensions of ancient temples, in musical tuning systems that predate modern standardization. Sereda claims he was told in a vision to add 432 days to October 19th, 2024. The result? December 25th, 2025, Christmas Day. The same day his calculations show 3I-ATLAS will reach its closest approach to Earth, while simultaneously achieving what he calls the Great Pyramid Angle, a specific geometric relationship between the object, Earth, and the angle encoded in the slope of the Great Pyramid at Giza. Let us pause here and acknowledge the obvious problem. This sounds insane. Visions, Fatima miracles, ancient pyramids, Fibonacci codes from interstellar objects. Every rational bone in your body should be screaming that this is numerology, pattern seeking, the human brain desperate to find meaning in randomness. And maybe it is. But here is what we cannot ignore. The light pulse observations, according to Sarita, occurred. He has published the data. The timing is verifiable, October 13th, 2025, exactly 108 years after Fatima. The trajectory calculations are verifiable. 3I-ATLAS will indeed be at its closest point to Earth on December the 25th. The geometric alignment he describes can be calculated and checked. The question is not whether Sarita is making things up. The question is whether what he observed is real, and if it is real, whether it means what he thinks it means. And here is where the timing gets uncomfortable. On October 13th, the same day Sarita reported these observations, NASA's Solar Dynamics Observatory experienced what the agency described as technical difficulties and stopped providing public data feeds. The spacecraft is designed to monitor the sun continuously, producing images and data that are normally available to the public in near real time. That feed went dark on October 13th. It has since come back online, but the gap exists during the precise window when Sarita claims to have observed the Fibonacci pulses. Could this be coincidence? Of course. Technical malfunctions happen, but the timing raises questions, especially when you consider what happened next. On October 1st, just 2 days before 3I-ATLAS made its closest approach to Mars, offering the best observation opportunity we've had or will have until it passes Jupiter in 2026, the United States government shut down. NASA furloughed more than 15,000 employees, 83% of its workforce. Only personnel deemed essential remained. The space agency's website stopped updating, and the high-resolution camera aboard the Mars Reconnaissance Orbiter, which was positioned to capture images of 3I-ATLAS with a resolution of 30 kilometers per pixel, the highest resolution images ever taken of this object. Those images have not been released to the public. ESA, the European Space Agency, released some images from its Mars orbiters on October 7th, 4 days after the flyby. The images show 3I-ATLAS as a fuzzy blob, qualitatively similar to what Hubble captured months earlier but from much closer range. They're interesting, but they do not provide the detail that HIRIS should have captured, and NASA has said nothing. Rep. Anna Paulina Luna publicly asked about the high-resolution images. White House Deputy Chief of Staff Stephen Miller was asked during an interview whether the president had been briefed on 3I-ATLAS. The question was deflected. Avi Loeb, in his Medium posts, has repeatedly mentioned that the high-resolution images would answer critical questions about the size and nature of this object, but as of today, October 20th, those images remain unreleased. So, we have Fibonacci pulses reported on October 13th, NASA's Solar Dynamics Observatory going dark the same day, the government shut down beginning 2 days before the critical Mars flyby, high-resolution images withheld, and Sarita connecting all of this to a prophetic timeline that points to Christmas Day 2025 as some kind of culmination point. It would be easy to dismiss this as conspiracy thinking if not for one uncomfortable fact. The other 7 anomalies are not speculation. They are documented, peer-reviewed, and they are forcing mainstream astronomers into intellectual contortions to explain them away. Sarita has built what he calls a hyperdimensional solar system model, a framework based on dividing the golden ratio into planetary orbital periods. According to this model, the rotational period of 3I-ATLAS, 16.16 hours, converts to 969.6 minutes. That number matches the age of Methuselah from the Bible, 969 years. When you divide 969.6 by Earth's exact sidereal period of 365.256,363 days, you get 2.65457388, which is the golden ratio squared with 99.5% accuracy. Sarita claims this is not coincidence. He claims 3I-ATLAS is encoding a message about the structure of the solar system itself. revealing the existence of hidden planets that orbit at positions defined by Fibonacci ratios. This is where most scientists would stop listening. Hyperdimensional hidden planets based on biblical numerology, and the golden ratio is not astronomy, it is mysticism dressed in mathematical clothing. But Sarita would counter that his model accurately predicts the orbital periods of known planets when you apply the Fibonacci sequence and golden ratio fractals. He claims that when you superimpose his model based on the number 591, which he associates with his wife Crystal, over the model based on 969.6 from 3I-ATLAS, the differences between corresponding numbers produce the Fibonacci sequence itself, and those numbers, he argues, correspond to planets, both visible and hidden. Whether Sarita's model has any validity is almost beside the point. What matters is this. On October 13th, he observed something. Light pulses in a pattern, 5, 8, 13. He published this observation on Medium the same day. The pattern matches the Fibonacci sequence. The date matches the Fatima anniversary exactly. The calculations pointing to Christmas Day are verifiable. You can check them yourself. And NASA's Solar Dynamics Observatory went offline during the observation window, while high-res images from the Mars flyby remain withheld during a government shutdown that began at the most inconvenient possible moment. Is Sarita correct in his interpretation? Is 3I-ATLAS broadcasting a mathematical message intended to reveal hidden planets in a solar system structure based on the golden ratio? That seems unlikely. But did he observe something real? Did something happen on October 13th that correlates with a 108-year anniversary of a mass-witnessed anomalous event? And does that something point toward December 25th as a date of significance? That is harder to dismiss. Think about what we are actually discussing here. We have an interstellar object, confirmed to have originated beyond our solar system, travelling on a trajectory that multiple scientists have calculated has a less than 1% probability of occurring by chance. This object is currently hidden directly behind the Sun, unreachable by ground-based telescopes, during the exact period when it reaches perihelion and would have maximum energy available for any kind of manoeuvre or activity. It will remain hidden until early November. When it emerges, we will be able to see if its trajectory has changed. We will be able to see if it has fragmented, releasing smaller objects. We will be able to see if it is still behaving like a comet or if something else is happening. And if Sarita is even partially correct, if there is any validity to the December 25th timeline, we have 65 days to prepare for whatever that might mean. 65 days to watch this object as it moves from perihelion back out through the solar system. 65 days to see if the pattern holds, if the Fibonacci message was real, if the timing is truly prophetic or merely the latest in a long line of apocalyptic predictions that amount to nothing. But here is the thing that keeps you awake. We have 65 days to watch, but only if NASA releases the data, only if the high-res images are made public, only if the global astronomical community can coordinate observations when 3I-ATLAS emerges from behind the Sun in November. And right now, during the most critical observation window we have had, during the exact week when this object is at perihelion receiving maximum solar energy, NASA is shut down, the best images are withheld, and the object is invisible to us. Coincidence? Maybe. But when coincidences stack this high, when the timing aligns this precisely, when the pattern fits this neatly, the word coincidence starts to feel inadequate. It starts to feel like a word we use when we do not want to confront the other possibilities. And those other possibilities, the ones we're about to explore through the remaining 7 anomalies, those possibilities are not comfortable. They're not safe. They challenge everything we think we know about our place in the cosmos, about whether we are alone, about whether we are being observed, studied, perhaps even contacted by something that understands mathematics and geometry and timing in ways that make our most advanced physics look like children counting on their fingers. The Fibonacci sequence. 5, 8, 13. Pulses of light from an object that should not exist, observed on a date that should not matter, pointing toward a future date that carries impossible significance. And all of it happening while we are blind, while the object hides behind the Sun, while the images that could answer our questions remain locked away behind a government shutdown and bureaucratic delays that strain credulity and their convenience. The government blackout, what are they hiding? October 1st, 2025. 2 days before 3I-ATLAS makes its closest approach to Mars, 2 days before the observation opportunity astronomers had been planning for months, 2 days before the high-risk camera would capture images with 30 km per pixel resolution, images that could finally tell us the true size and structure of this object. On that day, the United States government shut down. 15,300 NASA employees received furlough notices. 83% of the agency's civil servant workforce sent home. Only those deemed mission essential remained at their posts. The timing, as Avi Loeb noted with barely concealed frustration, could not have been worse. But here is what makes this more than just unfortunate timing. NASA initially stated that processing the Mars flyby data would require several days. Complex image processing, spectroscopic analysis, careful calibration and verification. These things take time. The agency set expectations appropriately. Then, on October 4th, less than 24 hours after the flyby, NASA provided selective briefings to mainstream media outlets. No images, no spectroscopic data, no technical reports. Just verbal characterizations describing 3I-ATLAS as an ordinary comet exhibiting normal cometary behavior. The message was clear. Nothing to see here. Move along. The problem? Those briefings directly contradicted what multiple independent observatories had been reporting for months. They contradicted the Hubble data showing the sun would jet. They contradicted the Keck telescope observations of extreme nickel emissions without iron. They contradicted Loeb's calculations showing the object must be extraordinarily massive to resist the rocket effect of its own outgassing. And they were delivered without any supporting evidence during a government shutdown before the highest resolution images had been processed or released. Convenient does not begin to describe it. ESA, the European Space Agency, took 4 days to release their first images from the ExoMars Trace Gas Orbiter. When those images appeared on October 7th, they showed 3I-ATLAS as expected, a fuzzy bright spot against the background of streaked stars, the camera tracking the comet's motion. The Cassius camera, with its 13.5 centimeter mirror, captured the brightest central region extending about 680 kilometers, qualitatively similar to what Hubble had seen months earlier, but from much closer range. The images confirmed outgassing. They confirmed activity. They confirmed that 3I-ATLAS is not just a dark rock silently passing through, but they did not provide the detail needed to resolve the core mysteries. That detail should have come from HiRISE, the high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter. This camera, with its half-meter primary mirror, was positioned perfectly for the October 3rd flyby. At a distance of 29 million kilometers, HiRISE's angular resolution translates to 30 kilometers per pixel. The brightest pixel in such an image would directly constrain the surface area of 3I-ATLAS's nucleus. With assumptions about albedo, that measurement would give us the size. And size matters because Loeb has calculated that if this object is larger than 5 kilometers in diameter, its mass becomes anomalous beyond any reasonable natural explanation. Think about what that means. Loeb's calculation of 33 billion tons, his minimum mass estimate based on the lack of non-gravitational acceleration, that is a lower bound. The object could be larger, could be heavier, and if HiRISE shows a nucleus significantly larger than 5 kilometers, we are no longer discussing whether 3I-ATLAS is unusual. We are discussing whether it can be natural at all. The statistical probability of an interstellar object this massive appearing in our solar system becomes vanishingly small. The reservoir of icy bodies in interstellar space simply does not predict objects of this scale travelling at these speeds showing up at our doorstep. So, where are the HiRISE images? 2.5 weeks after the flyby, as of today, October 20th, NASA has not released them. The agency claims processing delays. The shutdown disrupted workflows. Teams are understaffed. These explanations are plausible. Image processing does take time, especially when working with data from instruments millions of kilometers away. But the ESA managed to release their images within 4 days, despite having no shutdown to contend with. And NASA managed to brief media outlets within 24 hours, despite supposedly needing more time to process the actual data. The inconsistency raises questions. Pavel Zlatnik, writing on Medium, laid out what he calls the information playbook. The pattern, he argues, is textbook. When an image shows something difficult to explain, something that challenges the established narrative, there is a predictable sequence of institutional responses. First, delay. Processing takes time. We need to verify. We need to calibrate. Weeks can pass. Second, selective release. Brief trusted outlets verbally before showing anything publicly, control the narrative, frame the interpretation before people can see the raw data and form their own conclusions. Third, bureaucratic obstacles, government shutdowns, budget constraints, staffing issues, always plausible, never quite provable as intentional, but remarkably convenient in their timing. Is that what is happening here? Are we watching institutional obfuscation in real time, or are we watching normal scientific caution combined with genuinely bad timing? The answer matters because we are not talking about abstract scientific curiosities. We're talking about an object that multiple researchers have suggested might not be natural. We are talking about trajectory alignments, calculated at less than 1% probability. We're talking about chemical signatures never seen in nature, and we're talking about an observation window that is closing. Right now, 3I-ATLAS is behind the sun. We cannot see it. When it emerges in early November, if its trajectory has changed, if it has fragmented, if it has released smaller objects, we will need the baseline data from the Mars flyby to make sense of what we're seeing. Without those high-rise images, we are flying blind. The government shutdown officially ended on October 9th after 9 days of paralysis. House Speaker Mike Johnson told reporters the ball was in the Senate's court. The Senate vote to advance a continuing resolution failed, 54 to 45, 6 votes short of the 60 needed. Another vote, another failure, another delay. Meanwhile, NASA's website displayed a message stating the agency was closed due to lack of government funding. Employees could visit a specific shutdown information page, but public data feeds remained dark. The Mars Reconnaissance Orbiter continued to function, its autonomous systems operating as designed, but with no staff to process and release the data it collected, those observations might as well not exist. Rep. Anna Paulina Luna asked pointed questions. Was the president briefed on 3I-ATLAS? What information does the White House have about this object? White House Deputy Chief of Staff Stephen Miller deflected during his interview, discussing the shutdown in general terms without addressing 3I-ATLAS specifically. Avi Loeb mentioned the exchange in his writing, noting the absence of clear answers. The scientific community found itself in an uncomfortable position. They had data, somewhere, locked in computers and storage systems, but no mechanism to release it publicly, no staff to process it, no budget to fund the work. And here is where the conspiracy theories found fertile ground. Social media erupted with speculation. NASA knows what 3I-ATLAS is and they are hiding it. The government shut down on purpose to keep the truth from coming out. The high-res images show something impossible, something that would upend everything we think we know, and they cannot let us see it. These theories spread rapidly, amplified by the genuine strangeness of the timing, by the unexplained delays, by NASA's selective media briefings characterizing the object as ordinary without providing supporting evidence. Loeb, in his typical direct style, dismissed the conspiracy angle bluntly. The delay in data release, he wrote, does not signal extraterrestrial intelligence. It signals terrestrial stupidity. Large research teams take time to coordinate. Bureaucratic processes are slow. The government shutdown was real, not manufactured. Incompetence and bad luck, he argued, are far more common than conspiracies. But even Loeb acknowledged the frustration. We need that data, we need those images, and the longer we wait, the more the public trust erodes, the more the narrative gets controlled by speculation rather than evidence. Then came the Perseverance images. On October 4th at 21:33:39 Martian local solar time, NASA's Perseverance rover, sitting on the surface of Mars in Jezero crater, captured an image with its right navigation camera. The image shows an elongated streak against the blackness of the Martian night sky. Astrophotographer Simeon Schmaus stacked 20 images from the Mastcam Z camera and reported finding a faint smudge at the location where 3I-ATLAS should be visible. He posted his findings online. This, people said, this is 3I-ATLAS photographed from the surface of Mars. Look at the shape. Look at the elongation. It is not a fuzzy ball. It is a cylinder, an elongated structure. exactly what you would expect if this thing is artificial. Loeb addressed this immediately. The streak, he explained, is an artifact. The navcam has an angular resolution of 0.33 milliradians per pixel, which at the distance of 3I-ATLAS translates to about 12,500 kilometers. The elongated streak appears to be about 50,000 kilometers long based on its pixel dimensions. But the upper bound on 3I-ATLAS's actual diameter, as measured by SphereX, is 46 kilometers, assuming an albedo of 4%. The streak is 1,000 times longer than the object itself. What we are seeing, Loeb concluded, is motion blur. The camera's integration time, combined with the object moving across the Martian sky, creates the appearance of elongation. If 3I-ATLAS were actually 50,000 kilometers long, Hubble would have resolved it as an extended object months ago. It did not. Therefore, the streak is an imaging artifact, not evidence of a cylindrical megastructure. But NASA never officially confirmed this. The space agency posted the image on its multimedia page as Image of the Week for week 242. No caption explaining what it showed. No clarification that this might be Phobos, Mars's moon, rather than 3I-ATLAS. No technical breakdown of why the streak appears elongated. Just the image, raw and unexplained, left for public interpretation. And the public interpreted it exactly as you would expect. This is proof. NASA photographed an alien spacecraft and they are trying to hide it in plain sight. The silence became its own story. Why would NASA release an ambiguous image without context during a shutdown? Why brief media outlets verbally about normal cometary behavior while simultaneously posting an image that looks decidedly abnormal to untrained eyes? Why withhold the HiRISE data that could resolve all ambiguity while allowing speculation to spiral unchecked? If the goal was to maintain public trust and scientific credibility, these choices seem almost perfectly designed to achieve the opposite. And through it all, 3I-ATLAS continued its journey. It crossed through the observation window. It passed Mars. It moved toward Perihelion, and now it sits behind the Sun, invisible, unreachable, during the exact period when its behavior matters most. We will not see it again until November. When it emerges, we will look for changes, trajectory modifications, fragmentation, new objects that were not there before, but without the baseline data from the Mars flyby, without those HiRISE images, we will struggle to identify what is new versus what we simply failed to notice earlier. Loeb pointed out that the Mars flyby was observed by multiple spacecraft, not just NASA assets, but China's Tianwen-1, UAE's Hope orbiter with its Emirates Mars mission instruments, ESA's 2 orbiters. All of these platforms collected data. Some of that data has trickled out through ESA, but the highest resolution observations, the ones that matter most, those remain locked away behind a government shutdown, bureaucratic delays, and processing timelines that feel increasingly implausible as the weeks stretch on. The pattern Zlatnik described plays out before our eyes. Delay the data, control the narrative, frame the interpretation before releasing anything concrete. And if you're feeling generous, attribute it all to incompetence rather than intent. Either way, the result is the same. We do not know what 3I-ATLAS looks like up close. We do not know its true size. We do not know whether the chemical signatures are as anomalous as they appear, or if there is some conventional explanation we have not considered. And we will not know until NASA decides we are ready to know. The Sunward Jet, breaking physics. On August 2nd, 2025, the 2-meter twin telescope at Teide Observatory in the Canary Islands captured something that should not exist. 159 exposures, each 50 seconds long, stacked and processed to reveal faint details invisible to single snapshots. The resulting image showed 3I-ATLAS with a jet extending approximately 6,000 kilometers from its nucleus. But this jet was not pointing away from the Sun, pushed back by solar radiation pressure and the solar wind like every normal comet tail we have ever observed. This jet pointed toward the Sun. The technical term is anti-tail. The colloquial term is impossible. Comet tails form because the Sun blasts them with radiation and streams of charged particles, small dust grains, released as surface ice sublimates, get pushed away from the Sun by photon pressure. Gas molecules, ionized by ultraviolet radiation, get swept back by the solar wind. Everything moves away from the Sun. That is how tails work. That is how physics works. tail pointing toward the sun is like water flowing uphill, like smoke falling down instead of rising. It violates the basic mechanics that govern how matter behaves in space. Except it does not exactly. Anti-tails have been observed before, but they are rare and they have specific geometric explanations. Usually they appear when Earth's viewing angle aligns with the comet's orbital plane. We see a thin layer of debris left behind in the comet's orbit, edge on, creating the optical illusion of a tail pointing forward. It is not actually material moving toward the sun. It is material we are seeing from an unusual angle, perspective trick. But 3I-ATLAS was not in a geometric configuration that produces this effect. The viewing angle was only 10 degrees away from the direction of 3I-ATLAS relative to the sun. If you were looking sideways at a real Antares tail from orbital debris, you would see it stretched out long and thin. The 2-meter twin telescope image shows a jet that, when corrected for the 10-degree viewing angle, would be about 10 times longer than it is wide. Avi Loeb and Eric Quito published a paper analysing this geometry. They concluded that what we are seeing is not an optical illusion from viewing angle. It is actual material being ejected toward the sun from 3I-ATLAS itself. A jet. A directed outflow. And that raises two questions that nobody wants to answer. First, what physical mechanism could produce such a jet? Second, why are comet experts insisting this is normal while simultaneously having no conventional explanation for how it forms? The Hubble Space Telescope saw this same feature back on July 21st. At that time, 3I-ATLAS was 365 million kilometers from Earth. Hubble's image showed an extended glow ahead of the object, pointing in the direction of the sun. The image was published. Scientists looked at it, and many of them immediately declared victory. See? It has a tail. It is definitely a comet. But that initial enthusiasm glossed over a critical detail. The glow was pointing the wrong direction. When you correct for viewing angle, when you do the geometry properly, the feature is not a tail. It is a forward-facing jet, and forward in this case means sunward. Now, to be fair, sunward jets are not completely unknown. Comet C 2014 UN271, also known as Bernardinelli-Bernstein, showed a similar sunward enhancement when it was observed far from the sun. The explanation proposed in that case involved large dust particles ejected slowly from the sunlit hemisphere. These particles do not get blown back by radiation pressure because they are too massive. They move forward with the comet for a while before eventually drifting away. The key word is slow. Slow ejection, large particles, minimal forces. It creates a dust fan ahead of the comet that looks, from certain angles, like a sunward tail. Could this explain 3I-ATLAS? Possibly, but there are problems. First, 3I-ATLAS shows a rotation period of about 16 hours. If the sunward jet is coming from a localized hotspot on the rotating nucleus, that hotspot would rotate in and out of sunlight every 8 hours. The jet should pulse. It should vary in brightness and direction as the nucleus spins. But observations from SphereX show the dust plume extending out to 348,000 kilometers in a relatively stable configuration. That is not consistent with a rotating hotspot unless the hotspot happens to be positioned at one of the poles, constantly facing the sun. That would require a very specific orientation of the spin axis, unlikely but not impossible. Second, the composition is weird. Webb telescope data from August 6th shows the plume around 3I-ATLAS is dominated by carbon dioxide, with much lower levels of water and carbon monoxide. Carbon dioxide sublimes at lower temperatures than water ice. It would start out gassing farther from the sun. But 3I-ATLAS was already showing activity at 4.4 astronomical units, which is unusually far out for significant carbon dioxide outgassing. And if this is just large dust particles being slowly pushed forward, why is the chemical signature so unusual? Why so much carbon dioxide and so little water compared to every other comet we've studied? Third, there is the matter of collimation. The Hubble and 2-meter twin telescope images both show a feature that is elongated, roughly 10 times longer than it is wide. That degree of collimation suggests a directed outflow, not a diffuse cloud of slowly drifting dust. Jets form when gas escapes through vents or fissures in the nucleus surface. The escaping gas carries dust with it. If the vent is narrow, the jet is narrow. But a narrow vent on a rotating nucleus would produce a spiral pattern as the nucleus spins. We do not see that here. We see something straighter, more stable, more like a continuous outflow from a single direction. Put these pieces together and you get a picture that does not quite fit. A jet pointing toward the sun, stable enough to appear in multiple observations weeks apart, collimated enough to show a 10-to-1 axis ratio, chemically dominated by carbon dioxide in a configuration that suggests more than just passive dust scattering. Loeb and Quito argue this is anomalous. It deserves attention. It deserves an explanation that goes beyond just waving hands and saying comets are weird sometimes. Jason Wright, an astronomer at Penn State, pushed back hard on this characterization. In a blog post, he pointed out that Loeb and Quito are not the first or only researchers to describe this phenomenon. Other teams have published papers discussing the sunward enhancement in 3I-ATLAS, using similar physical explanations. Farnham and colleagues described it as slow ejection of large particles from the sunlit hemisphere. Wright argues that Loeb is claiming uniqueness where none exists, framing a moderately unusual but not unprecedented feature, as if it is revolutionary evidence of something artificial. Wright also notes that the rotation period complicates any simple model. If 3I-ATLAS is rotating every 16 hours and the dust plume extends hundreds of thousands of kilometers, then the hotspot generating the plume cannot be stationary, it must be moving. That would generate mechanical effects, torques, changes in the outflow pattern that we are not seeing or at least not clearly resolving yet. Oumuamua had a tumbling light curve that did not repeat exactly, suggesting complex rotational dynamics. If 3I-ATLAS is similarly complex, trying to model its dust distribution based on a simple assumption of a single static vent is probably naive. So, who is right? Is the sunward jet an unprecedented anomaly that demands exotic explanations? Or is it a moderately unusual but naturally explainable feature that Loeb is hyping for attention? The frustrating answer is we do not have enough data to say definitively. What we know is this. 3I-ATLAS has a feature ahead of it that points toward the sun. That feature has been observed by Hubble, by the 2-meter twin telescope, and confirmed by spectroscopic observations from Keck. The feature is collimated, roughly 10-to-1 length-to-width ratio. It is chemically dominated by carbon dioxide, and it appears stable over weeks of observation despite the nucleus rotating every 16 hours. Conventional explanations exist. Large dust particles, specific rotation axis orientation, slow ejection from a sunlit hotspot. These mechanisms can, in theory, produce what we are seeing, but they require specific conditions. They require the spin axis to be aligned just right. They require the composition to be unusual in just the right way. They require multiple low probability factors to all be true simultaneously, and when you stack low probability explanations, you start to wonder if you're working too hard to make the data fit your preferred conclusion. Here is what makes this particularly interesting. Anti-tails, when they do appear, are usually short-lived. They are geometric effects visible for a few days or weeks as Earth passes through the comet's orbital plane. The fact that 3I-ATLAS has maintained this feature over months, from July through August and into September, suggests it is not a perspective trick. It is real material, really positioned ahead of the nucleus, really pointing toward the sun, and real material pointing toward the sun requires a physical mechanism to put it there and keep it there. One possibility nobody wants to discuss seriously is thrust. If 3I-ATLAS is venting material preferentially from its sun-facing side, that creates a rocket effect. Gas escaping in one direction pushes the object in the opposite direction. For a natural comet, this thrust is usually small and chaotic, varying as different parts of the surface heat up and cool down with the rotation. But if the venting is concentrated, if it is coming from a specific region that remains sun-facing, the thrust could be more directed, and directed thrust is indistinguishable, observationally, from a propulsion system. Loeb has been careful not to claim definitively that 3I-ATLAS is artificial. He uses phrases like warrants investigation and cannot be ruled out. He assigns it a rank of 4 on his personal scale, where 0 is definitely natural and 10 is definitely artificial. 4 means genuinely anomalous but not conclusive. It means this object exhibits multiple features that do not fit neatly into our understanding of natural comets, but it is not so weird that we have to abandon natural explanations entirely, not yet. The sunward jet is one piece of a larger puzzle. In isolation, you could explain it away. Unusual, but not impossible. Weird geometry, weird composition, weird timing, but all within the realm of natural phenomena if you're willing to grant multiple unlikely coincidences. But the sunward jet is not in isolation. It is one of 8 anomalies, and when you start stacking anomalies, when you start requiring coincidence after coincidence after coincidence, the natural explanation starts to feel forced. It starts to feel like motivated reasoning, like clinging to the comfortable answer because the uncomfortable answer is too strange to contemplate. On August 27th, the Gemini South telescope finally detected a normal antisolar tail, a faint teardrop shape pointing away from the sun as expected. This was presented as evidence that 3I-ATLAS is behaving like a comet after all. See? It has a normal tail now. But the timing is interesting. 3I-ATLAS had been showing only the sunward jet for months. Then, as it got closer to the sun and heated up more, a conventional tail appeared. The sunward jet did not disappear, it was joined by a normal tail, so now we have both. A jet pointing toward the sun and a tail pointing away from the sun, simultaneously. If this is natural, if this is just unusual comet behaviour, why did it take so long for the normal tail to develop? Why did the sunward jet appear first and persist even after the normal tail formed? These are the questions that do not have satisfying answers yet. These are the observations that make you pause, that make you look twice, that make you wonder if we're seeing something we have never seen before because it is something that should not exist. A comet with a tail coming out of its forehead, as Loeb colourfully described it. An object that seems determined to break the rules just enough to be unsettling but not quite enough to be definitive. And through it all, the nagging question. If this is natural, why does it require so much explaining? Why do we need multiple papers, competing theories, careful geometric analysis, and special pleading about rotation axes and dust grain sizes? When something is genuinely ordinary, it does not take this much effort to make it fit. The industrial metal mystery. On August 24th, 2025, the Keck 2 telescope in Hawaii turned its cosmic web imager toward 3I-ATLAS. The resulting spectroscopic data, published in a paper by W.B. Hugendam and colleagues, revealed something that has never been observed in any natural celestial body in the history of astronomy. The gas plume surrounding 3I-ATLAS shows prominent emission lines from neutral nickel atoms. Strong, clear, unmistakable, and those nickel emissions appear without corresponding iron emissions. In every other comet ever studied, nickel and iron appear together in roughly consistent ratios. They are bound together in the minerals that make up cometary nuclei. They vaporize together when the surface heats. They appear together in the spectra, always, until now. The Keck data shows nickel emission that is orders of magnitude stronger than what appears in typical solar system comets. Not a little more, not twice as much. Orders of magnitude, and the iron that should accompany it, absent. Not reduced, not faint. Absent. This is not a quirk of composition. This is not unusual, but natural variation. This is a chemical signature that does not occur in nature. The paper states this explicitly. The production rate of nickel relative to cyanide is higher than in 2I Borisov and orders of magnitude above the solar system comet median. The presence of nickel without iron in these quantities has one known analogue: industrial nickel refining through the carbonyl chemical pathway. Let us be very clear about what we are discussing. Nickel tetracarbonyl, chemical formula NiCO4, is a compound used in industrial processes to purify nickel metal. You produce it by exposing impure nickel to carbon monoxide gas at moderate temperatures. The nickel reacts with the carbon monoxide to form nickel tetracarbonyl, a volatile liquid that can be separated from impurities. Then you heat it up, it decomposes back into pure nickel and carbon monoxide. This process, called the Mond process, is how humans refine nickel. It is a technology we invented. It does not occur in nature because nature does not have the precise temperature and pressure conditions, the controlled atmospheres, the engineered systems required to make it happen consistently. And yet, here we are, looking at spectroscopic data from an interstellar object showing nickel emissions consistent with carbonyl decomposition, appearing without the iron contamination you would expect from natural mineral sources. The paper mentions this. Other than 3I-ATLAS, the anomaly of nickel without iron was only known to exist in industrially produced nickel alloys, not in comets, not in asteroids, not in interplanetary dust, in human-made materials, and now apparently in an object that travelled here from another star system. The immediate objection is obvious. This cannot possibly mean what it appears to mean. There must be a natural process we do not understand yet, some exotic chemistry happening on the surface of 3I-ATLAS that happens to mimic industrial nickel refining by pure coincidence. And maybe that is true. But what would that process be? How do you get nickel vaporizing without iron in a natural environment? The paper from the Very Large Telescope team, using the UVES spectrograph, addressed this directly. At the distances where comets are observed, the temperature is far too low to vaporize silicate, sulfide, and metallic grains that contain nickel and iron atoms. Therefore, the presence of nickel and iron atoms in cometary coma is extremely puzzling. They go on to note that 3I-ATLAS, which is a C2 depleted comet, exhibits extreme properties in the early phases of its activity with regard to the production rates and abundance ratios of nickel and iron. C2 depleted means low in diatomic carbon molecules, another unusual characteristic. The combination of C2 depletion, extreme nickel production, and the absence of iron creates a chemical profile unlike anything documented in natural bodies. The Very Large Telescope team does not speculate about artificial origins. They note the anomaly, describe it carefully, and leave it at that. But the implication hangs in the air, unspoken but impossible to ignore. If this composition is natural, it requires mechanisms we do not currently understand. And if we do not understand the mechanisms, how confident can we be that they are natural? The Keck images show something else interesting. They captured narrow-band photographs isolating the emission from cyanide and from nickel. Both emissions show asymmetric profiles extending in both the solar and antisolar directions. The nickel distribution follows a similar pattern to the cyanide, but the nickel-to-cyanide ratio is much higher than in 2I Borisov or any solar system comet. And the white light image, which shows scattered sunlight from dust particles, does not reveal a normal cometary tail. The dust scattering pattern is inconsistent with radiation pressure pushing small particles away from the sun. Instead, the distribution looks more like the material is being released in multiple directions without a clear preferential backflow. Now, cyanide itself is not unusual in comets. Cyanogen, CN, is a common cometary emission. It forms when ultraviolet light breaks apart larger organic molecules on the comet's surface. What is unusual is the ratio. Too much nickel relative to the cyanide, and that ratio matters because it tells you something about what is vaporizing from the surface. If you're seeing typical cometary ices sublimating, you get typical cometary ratios. If you're seeing something else, some other process releasing material into the coma, the ratios shift. And the ratios here are shifted far outside the normal range. Loeb has been pointing to this as a key piece of evidence. He notes that nickel tetracarbonyl can be created through the carbonyl process, which refines nickel through the formation and decomposition of this compound. The fact that we see nickel without iron suggests the source of the nickel is not mixed mineral grains that would contain both metals together. It suggests a refined source, something that has been processed to separate the nickel from other elements, and the only known processes that do this separation are industrial. Critics argue that Loeb is cherry-picking. Yes, the nickel-iron ratio is unusual. Yes, the composition is weird. But jumping from unusual composition to industrial refining to alien technology is a leap across multiple chasms of uncertainty. There could be natural processes involving temperature gradients, partial melting, differentiation in the parent body, preferential vaporization at specific temperatures, all sorts of geochemical mechanisms that might produce this effect. We have only studied 3 interstellar objects. We have only taken detailed spectra of 2. Our sample size is pathetically small. Declaring that 3I-ATLAS must be artificial because its composition does not match the dozen or so solar system comets we have studied in detail is premature. This is a fair criticism. We are extrapolating from very limited data. But here is the counter-argument. Science proceeds by recognizing patterns and investigating anomalies. If you find something that does not fit the pattern, you have 3 choices. First, expand your understanding to accommodate the new observation. Second, gather more data to determine if the anomaly is real or instrumental error. Third, ignore it and hope it goes away. The scientific community seems split between options 1 and 3, with very few people enthusiastically pursuing option 2. Expanding our understanding might mean proposing new geochemical mechanisms that can produce nickel without iron in cometary environments. Great. Propose them. Model them. Show us the conditions required and explain why those conditions would exist on an interstellar comet but not on solar system comets. So far, nobody has done this convincingly. The papers note the anomaly, describe it as extremely puzzling, and then move on without providing a satisfying natural explanation. That is not science expanding to accommodate new observations. That is science describing observations and then shrugging. Gathering more data is the obvious solution. We need more spectra. We need observations at different wavelengths. We need to track how the emissions change as 3I-ATLAS moves closer to and then away from the Sun. The JUICE spacecraft is scheduled to observe 3I-ATLAS in early November. The Juno spacecraft will have an opportunity in March 2026, when 3I-ATLAS passes Jupiter. These observations might give us the data needed to resolve the mystery, but until then, we are stuck with what we have, and what we have is a chemical signature that looks industrial. The third option, ignoring it, seems to be the most popular. Many astronomers have simply decided that 3I-ATLAS is a comet, case closed, and any anomalies are just natural variation that will eventually be explained by normal processes once we understand comets better. This is motivated reasoning. It starts with the conclusion 3I-ATLAS is natural and works backward to fit the data. When the data does not fit well, the response is not to question the conclusion, but to invent increasingly elaborate scenarios that allow the conclusion to remain intact. Here is what we know for certain. 3I-ATLAS is emitting approximately 4 grams of nickel per second. It is emitting this nickel without corresponding ion emissions. The nickel to cyanide ratio is orders of magnitude higher than any known comet. The chemical signature is consistent with nickel carbonyl decomposition, a process used in industrial refining. These are facts, they are measurements, they're reproducible by any observatory with the appropriate instruments. What we do not know is what these facts mean. Do they indicate an unknown natural process? Probably, if we're being honest about base rates and prior probabilities. Most weird things in space turn out to be natural once we understand them better. But do they indicate something that warrants serious investigation and a willingness to consider uncomfortable possibilities? Absolutely. And this is where the scientific community seems to be failing. There is a reflexive dismissal, a knee-jerk insistence that this must be natural, that even suggesting otherwise is unscientific. But science is supposed to follow the evidence wherever it leads, and the evidence here is leading to uncomfortable places. Imagine for a moment that we discovered these same chemical signatures in a sample returned from Mars. Nickel without iron, ratios consistent with industrial refining processes, compounds that require specific temperatures and pressures to form. We would be having a very different conversation. We would be talking about possible contamination from Earth, yes, but we would also be seriously considering whether these signatures indicate some kind of activity, geological or otherwise, that we need to understand. We would not simply wave our hands and say Mars is weird sometimes. But because 3I-ATLAS is moving, because it is far away, because considering the alternative is so uncomfortable and carries so much baggage, we default to natural explanations even when those explanations are incomplete and unsatisfying. We tell ourselves that space is big and weird things happen, and we do not understand everything yet, so this is probably just another weird thing that will make sense eventually. And maybe it will. But maybe, just maybe, we are looking at something genuinely anomalous. Something that should not exist if our understanding of natural processes is correct. Something that requires us to either expand that understanding in radical ways or consider possibilities we have spent decades dismissing as fringe nonsense. The nickel without iron, the carbonyl signature, the industrial refining process analogue. These details do not prove anything, but they sure as hell suggest that something interesting is happening. Something worth investigating with more than just casual curiosity and pre-formed conclusions. The Keck data is publicly available. Anyone with the right equipment and expertise can verify the measurements. The question is whether anyone will do so with an open mind, willing to consider all possibilities, or whether we have already decided what 3I-ATLAS must be and are now simply waiting for the data to catch up with our assumptions. The perfect trajectory, mathematically impossible. Interstellar space is three-dimensional. Objects ejected from other star systems can approach our solar system from any direction. Up, down, sideways, any angle relative to the plane where our planets orbit. The ecliptic plane, the flat disk where Earth, Mars, Venus, Jupiter and the others circle the Sun, represents a tiny slice of possible approach vectors. If interstellar objects arrive randomly, most of them should come in at steep angles, diving through the solar system well above or below the planetary plane. Some would align closer to the ecliptic by chance, but the probability of any given object coming in nearly flat within just a few degrees of the planetary orbits is very small. 3I-ATLAS arrived within 5 degrees of the ecliptic plane. Its orbital inclination, the angle between its trajectory and the plane of planetary orbits, measures 4.89 degrees. That is remarkably flat. Loeb calculated the probability of this occurring by random chance for an object from interstellar space. The math is straightforward. The solid angle subtended by a 5-degree cone around the ecliptic, divided by the full sphere of possible approach directions, gives you the probability. The result? Approximately 0.2%, 1 in 500. Now, 1 in 500 sounds unlikely but not impossible. Rare things happen. If you observe 500 interstellar objects, one of them should statistically arrive within 5 degrees of the ecliptic. The problem is we have only observed 3 interstellar objects total: 1I Oumuamua, 2I Borisov, and 3I-ATLAS. Oumuamua came in at a much steeper angle, about 26 degrees. Borisov was even steeper, around 44 degrees. So out of our sample of 3, the first 2 arrived at angles you would expect for random interstellar wanderers. The third one, 3I-ATLAS, just happens to be the statistical outlier that arrives almost perfectly aligned with the planetary plane. Unlikely? Yes. Impossible? No. But wait, there is more. 3I-ATLAS is not just aligned with the ecliptic, it is moving retrograde, opposite to the direction that planets orbit. This is not particularly unusual in itself. Interstellar objects can arrive from any direction, including retrograde. What is unusual is the timing. 3I-ATLAS arrived at a moment when its retrograde trajectory would carry it past Mars, Venus and Jupiter, all within a relatively short span of time, all within tens of millions of kilometers. The object passed within 30 million kilometers of Mars on October 3rd. It will pass within a similar distance of Venus and Jupiter in the coming months. These close approaches are not accidents of trajectory. They're built into the orbital mechanics of something arriving flat and retrograde at this specific time. Loeb calculated the probability of this timing. Not just arriving flat, but arriving flat at exactly the right moment to pass near multiple planets due to the retrograde motion. His estimate? 0.005%. 5 in 100,000. Now we are stacking probabilities. Flat trajectory, 1 in 500. Arriving at the right time for planetary encounters, 1 in 20,000. Combined? We're approaching 1 in 10 million territory. At that point, you start to question whether random chance is an adequate explanation. But the stacking does not stop there. The arrival direction of 3I-ATLAS aligns within 9 degrees of the direction from which the famous WOW signal was detected on August 15th, 1977. For those unfamiliar, the WOW signal was a powerful narrowband radio signal detected by the Big Ear telescope at Ohio State University. Astronomer Jerry Amon saw it in the data printout and wrote WOW in the margin, giving the signal its name. The signal lasted 72 seconds, the maximum duration the telescope could observe a source as Earth's rotation carried it across the sky. It was never detected again despite repeated searches. Its origin remains unexplained. The signal came from the direction of the constellation Sagittarius, near the border with Scorpius. 3I-ATLAS also came from the direction of Sagittarius. The angular separation between the two directions is approximately 9 degrees. That might sound like a large separation, but in galactic terms, it is a tiny sliver of sky. The probability of an interstellar object arriving from within 9 degrees of a specific direction, chosen at random, is about 0.6%, 1 in 167. So now we have 3 low probability events. Flat trajectory, 1 in 500. Timed arrival for planetary encounters, 1 in 20,000. Arrival direction matching the WOW signal, 1 in 167. If these were independent probabilities, you would multiply them. The result would be vanishingly small, well into the billions to 1 range. But they are not entirely independent. The flat trajectory and the timed arrival are related. The retrograde path at low inclination is what creates the planetary encounter opportunities. So you cannot just multiply all 3. But even being conservative, even accounting for correlations, you are looking at combined odds well below 1 in a million. At what point do we stop calling this coincidence? At what point do we acknowledge that random chance is not a satisfying explanation for a cluster of improbable features? Loeb argues that we are past that point. He ranks 3I-ATLAS as a 4 on his scale specifically because these trajectory features, combined with the chemical and physical anomalies, create a pattern that strains credulity if we insist it all happened by accident. Critics respond that we are suffering from selection bias. We notice improbable features because they are interesting. We do not notice all the unremarkable interstellar objects that pass through without anyone detecting them, because they were too faint or too fast, or arrived at bad times for observation. If thousands of interstellar objects pass through the solar system every year, as some models suggest, then finding one with an unusual trajectory is not surprising. It is expected. The surprise is only that this one happened to be bright enough and close enough for us to study in detail. This is a fair point, but it has limits. Yes, detection bias is real. Yes, we tend to study the unusual cases because those are the ones we can see and reach. But detection bias explains why we might find an object with one unusual feature. It does not easily explain why the object we found has multiple unusual features all at once. The flat trajectory, fine. Maybe we happened to catch the rare one that came in flat. The planetary encounter timing, okay, maybe that is also luck. The WOW signal alignment, sure, another coincidence. The sunward jet, the nickel emissions, the extreme mass, the rotation period matching golden ratio relationships according to Sarida's model. All of it just happening to occur in this one object that we happen to observe? At some point, you have to ask if detection bias is doing all the heavy lifting, or if there is something genuinely anomalous about this particular object. Here is another angle. If 3I-ATLAS wanted to study the inner solar system, if it were a probe designed to collect data on multiple planets, what trajectory would you choose? You would want to come in flat so you pass through the region where the planets orbit. You would want a retrograde path so the planets come to you as they orbit, maximizing encounter opportunities. You would time your arrival so you pass Mars, Earth's orbit, Venus and Jupiter in succession. You would not waste energy fighting the sun's gravity to reach these targets individually. You would use ballistic trajectories and gravity assists, letting the sun's pull guide you efficiently from one encounter to the next. The trajectory of 3I-ATLAS, whether by design or accident, is nearly optimal for this purpose. It is not perfect. It does not pass extremely close to Earth, for instance. But it is far more efficient than a random arrival would be. And that efficiency, combined with the low probability of the trajectory occurring naturally, creates the uncomfortable question. Are we looking at the result of engineering? Are we looking at a path calculated to maximize scientific return while minimizing energy expenditure? Or are we looking at the luckiest coincidence in the history of interstellar astronomy? Now, here's where things get speculative in ways that demand attention. 3I-ATLAS reached solar conjunction yesterday. It is now directly behind the Sun, invisible from Earth. It will reach Perihelion on October the 29th, 8 days from today. Perihelion is the moment of closest approach to the Sun, the moment when gravitational potential energy is minimized, the moment when any propulsive maneuver would be most efficient due to the Oberth effect. If you wanted to change your trajectory, to add velocity or remove velocity or change direction, you would do it at perihelion. Every spacecraft mission that uses gravity assists knows this. You burn your engines at the lowest point in the gravity well to maximize the energy gain. If 3I-ATLAS is natural, we would expect nothing to happen at perihelion beyond increased outgassing as the surface heats up. If it is artificial, if it has any kind of propulsion capability, perihelion is when we would see it used. And the object is currently hidden from view. We cannot watch. We cannot monitor. When 3I-ATLAS emerges from behind the Sun in early November, we will see where it is and calculate where it should be based on gravitational predictions. If the two match, nothing unusual happened. If they do not match, if there is any deviation from the expected path, we will know something exerted force during the hidden period. This is not speculation. This is predictive. We can calculate right now where 3I-ATLAS should be on November 10th based purely on gravity. When we observe it on November 10th, we will measure where it actually is. Any discrepancy indicates non-gravitational acceleration. Outgassing can produce this, yes, but Loeb already calculated that the lack of non-gravitational acceleration up to September implies an extremely massive object. If sudden acceleration appears after perihelion, after months of showing no detectable thrust despite significant outgassing, that would be anomalous. That would require explanation. The other possibility is fragmentation. Natural comets sometimes break up as they approach the Sun. Thermal stress, rotation, tidal forces. These can crack a weakly bound nucleus into smaller pieces. If 3I-ATLAS is a comet, it might fragment. We would see multiple objects where there was one before. But if it is a mothership, if the speculation about releasing mini-probes has any validity, fragmentation would look very different. The pieces would not drift apart randomly. They would separate with purpose, each on a trajectory toward a different target. Telling these scenarios apart would require careful observation of the fragment trajectories over weeks and months. Loeb has suggested that if 3I-ATLAS releases probes at perihelion, they could use the Oberth effect to reach planetary targets with minimal velocity change. A probe ejected from the main body with a velocity of 30 to 40 km per second, applied at perihelion, could intercept Earth between late December and early January. The timing matches Sarita's Christmas Day prediction, though arrived at through completely different reasoning. Sarita talks about Fibonacci codes and Fatima anniversaries and Great Pyramid angles. Loeb talks about orbital mechanics and Oberth maneuvers. Both point to late December as a critical period. Coincidence or convergence? When different analytical approaches arrive at similar timelines, it either means the pattern is real or it means we're all fooling ourselves in similar ways. The next 70 days will tell us which. Right now, 3I-ATLAS is at the moment of maximum solar energy input. Right now, it is invisible. Right now, if anything is going to happen, this is when it would happen. And we are not watching. We cannot watch. All we can do is wait for it to emerge and see if the universe has decided to surprise us yet again. The impossible mass, Manhattan-sized visitor. When a comet releases gas and dust from its surface, physics demands a response. Action and reaction. The escaping material carries momentum. That momentum has to come from somewhere. It comes from the comet itself. The comet gets pushed in the opposite direction of the outflow, like a leaky balloon flying around a room. Astronomers call this non-gravitational acceleration. It is subtle, barely measurable for large comets, but it is real. Over weeks and months, a venting comet will drift slightly off the trajectory predicted by gravity alone. You measure the position, compare it to where gravity says it should be, and the difference tells you how much thrust the outgassing is producing. Avi Loeb looked at the orbital data for 3I-ATLAS spanning from May 15th through September the 23rd, 2025. 4.5 months of tracking. During that time, 3I-ATLAS was actively outgassing. Webb telescope observations confirmed carbon dioxide sublimating from the surface at a rate of 150 kilograms per second, with an outflow velocity of 440 meters per second. That is significant mass loss. That is significant momentum. The comet should be feeling thrust. It should be deviating from a purely gravitational path. But it was not. The measured positions matched the gravitational predictions within the error bars. No detectable non-gravitational acceleration. This presents a problem. If you're losing 150 kilograms per second at 440 meters per second, you're generating thrust. Conservation of momentum is not optional. The thrust is happening. So why is the trajectory not changing? There is only one answer. The object is so massive that the thrust is negligible. The force is real, but the acceleration is too small to measure because mass is in the denominator. Force equals mass times acceleration. Rearrange that. Acceleration equals force divided by mass. If mass is huge, acceleration is tiny. Make the mass huge enough, and the acceleration drops below detection limits. Loeb did the calculation. He took the upper limit on position deviation 0.028 arc seconds over 4.5 months. He converted that to a maximum acceleration. Then he took the known thrust from the outgassing, 150 kilograms per second times 440 meters per second equals 66,000 newtons of force. Divide the force by the maximum allowed acceleration, and you get a minimum mass. The result? 33 billion tons. That is the lower bound. 3I-ATLAS must weigh at least 33 billion tons, or we would have seen it drift off course. 33 billion tons. To put that in perspective, if you assume this is solid ice at typical cometary density of about 600 kilograms per cubic meter, you need a sphere roughly 5 kilometers in diameter. 5 kilometers, the width of Manhattan Island. The first interstellar object, Oumuamua, was estimated at 100 meters, maybe 200 at most. 2I Borisov was perhaps a kilometer. 3I-ATLAS is at minimum 5 kilometers, possibly larger. It is 1,000,000 times more massive than Oumuamua. It is 1,000 times more massive than Borisov, and it is moving faster than both. This is where the statistics become uncomfortable. Interstellar objects are not uniformly distributed by size. Smaller objects are far more common than larger ones. The size distribution follows a power law. For every giant comet, there are thousands of small ones. The probability of detecting a small interstellar object versus a giant one depends on brightness, which scales with surface area, which scales with radius squared. A 5-kilometer object has 25 times the surface area of a 1-kilometer object, so it reflects 25 times more sunlight. That makes it easier to detect at a given distance, yes, but it does not overcome the rarity problem. There are so many more small objects that, even accounting for detection bias, you expect to find small ones first. We found Oumuamua first. Small, dim, fast-moving, barely caught as it was leaving. We found Borisov second, medium size, clearly a comet, active and bright. Both fit expectations. Then we found 3I-ATLAS, massive, bright, and arriving on a trajectory that should be vanishingly rare. If you assume interstellar objects arrive randomly from the galactic reservoir of ejected planetesimals, finding a 5-kilometer giant as only your third detection is strange. The numbers do not add up well. Loeb has argued repeatedly that 3I-ATLAS, if confirmed to be this massive, represents a statistical anomaly that demands explanation. Either the interstellar population of large objects is much higher than models predict, or 3I-ATLAS is not a random sample from that population. If it is not random, what is it? A deliberately sent object? A rare survivor from an early era of planetary formation? A fragment of something larger that broke apart in interstellar space? Each of these scenarios has problems, each requires special pleading. The high-res images would resolve this. The camera resolution at the distance of the Mars flyby translates to 30 kilometers per pixel. The brightest pixel in the image would tell you the nucleus size directly. If the nucleus occupies 1 pixel, and that pixel is saturated bright white, then the nucleus is at least 30 kilometers across. That would be enormous, far larger than the 5-kilometer minimum from Loeb's mass calculation. It would be so anomalous that natural origins become almost untenable. If the nucleus occupies 1 pixel, but is not saturated, you can estimate the area from the brightness, assuming some albedo value. If the nucleus occupies multiple pixels, you can measure it directly. Any of these outcomes would constrain the size tightly. But we do not have the high-res images. We do not know if they show a 1-pixel bright dot, a multi-pixel extended source, or something else entirely. We are left with indirect constraints. The mass must be at least 33 billion tons. The diameter must be at least 5 kilometers. It could be larger, it could be much larger, and the larger it is, the harder it is to explain. Here's another constraint from SphereX. The Space Telescope observed 3I-ATLAS in August and measured its brightness. Assuming an albedo of 4%, which is typical for comets, the maximum diameter comes out to 46 kilometers. That is the upper limit. Anything larger and the object would reflect too much sunlight. It would appear brighter than observed. So we have a range, at least 5 kilometers from the mass calculation, at most 46 kilometers from the brightness measurement. The true size is somewhere in that range. 5 kilometers is already anomalous. 46 kilometers is absurd. If 3I-ATLAS is toward the upper end of that range, if it is tens of kilometers across, it is not just large. It is in a different category entirely. Objects that size are not comets. They are dwarf planets. They are large enough to have experienced significant internal evolution, differentiation, possibly even melting and reformation. And they are not supposed to be wandering through interstellar space at hyperbolic velocities. Think about how objects get ejected from star systems. Planets form from disks of gas and dust around young stars. Most of the material ends up in planets or gets blown away by stellar wind. A small fraction, the icy bodies in the outer regions, remains loosely bound. These are comets, asteroids, Kuiper belt objects. Occasionally, gravitational interactions with giant planets kick some of these objects onto escape trajectories. They leave the star system and drift through the galaxy. This ejection process favours smaller objects. A close encounter with a planet can easily fling a kilometre-sized comet into interstellar space. Flinging a 5-kilometre object requires more energy. Flinging a 46-kilometre object requires a very specific, very violent interaction. The larger the object, the less likely it is to be ejected cleanly. Instead of being thrown out, it is more likely to be perturbed into a different orbit within the system, or shattered by tidal forces, or captured by the planet. Getting a truly large object tens of kilometres across, ejected intact and at high velocity is difficult. Not impossible, but difficult enough that they should be rare in the interstellar population. And yet here we are, apparently looking at one. Loeb has noted that if the high-risk data confirms a diameter significantly larger than 5 kilometres, the natural origin hypothesis faces serious trouble. The statistical improbability of finding such an object, combined with the trajectory alignment and chemical anomalies, would stack enough coincidences that artificial origin would have to be considered seriously. Not as the only explanation, but as a hypothesis worthy of rigorous investigation rather than reflexive dismissal. The mass also relates to the sunward jet. A massive object is harder to push around. If 3I-ATLAS is truly 33 billion tons or more, the outgassing that creates the sunward jet is not going to change its trajectory much. It can maintain a stable, collimated jet for weeks without the thrust causing noticeable acceleration. A lighter object would start tumbling, would develop complex rotation, would show signs of the asymmetric thrust affecting its motion. 3I-ATLAS does not show these signs. It rotates steadily 16.16 hours, like a solid body under minimal torque. That stability is easier to explain if the object is massive. But massive comets are supposed to be rare. Massive interstellar objects are supposed to be vanishingly rare. And massive interstellar objects arriving on trajectories with less than 1% probability, while exhibiting chemical signatures never before observed in nature, those are supposed to be impossible. Yet here we are, describing observations, published data, peer-reviewed measurements, all pointing to something that should not exist. The minimum mass of 33 billion tons is not speculation. It is a calculation based on measured data. The absence of non-gravitational acceleration is observed. The outgassing rate and velocity are measured by Webb. The math is straightforward. Anyone can verify it. The conclusion is uncomfortable, but the conclusion is forced by the data. Either 3I-ATLAS is at least 5 kilometres in diameter and extraordinarily massive, or there is something wrong with our measurements. And if there is something wrong with our measurements, it would have to be a systematic error affecting multiple independent observatories using different instruments. That seems unlikely. So, we provisionally accept that 3I-ATLAS is massive, at least 5 kilometres, possibly much larger, and we ask what that means. If it is a natural comet, it is the largest interstellar comet we have ever seen by a huge margin. If it is not a comet, if the composition and behaviour suggest something else, then we are looking at an interstellar object of a type we have never encountered before, an object massive enough to resist the forces acting on it, an object large enough to potentially have internal structure, compartments, systems, an object that could in principle house instruments, power sources, propulsion, or whatever you might want to pack into a 5 to 46 kilometre shell. This is uncomfortable territory. We are edging towards science fiction concepts. Massive interstellar probes, generation ships, slow-moving exploration platforms designed to travel for thousands or millions of years between stars. These are ideas from novels and speculative papers, not from observational astronomy. But if the data pushes us here, if the measurements genuinely indicate something this large moving this fast on this unlikely trajectory, then we cannot dismiss the ideas just because they feel like fiction. Fiction is often just reality we have not encountered yet. The high-resolution images remain the key. When they are released, if they are released, we will know. We will see the nucleus size directly. We will confirm or rule out the extreme mass scenario. Until then, we have the calculation. 33 billion tons minimum, 5 kilometers diameter minimum, an object massive enough to shrug off the forces that would perturb a normal comet, an object that, by rights, should not be here, and yet it is, hiding behind the sun right now, unreachable, unobservable, waiting. Today's critical moment, solar conjunction and perihelion, October 21st, 2025. today. Right now, as you listen to this, 3I-ATLAS is positioned directly on the opposite side of the Sun from Earth. Solar conjunction. The Sun sits between us and the object, a massive glowing barrier that makes observation impossible. Ground-based telescopes cannot point at it without pointing at the Sun, which would damage instruments and reveal nothing but solar glare. Space-based telescopes face the same limitation. The geometry simply does not allow us to see what is happening. For the next week, possibly longer depending on solar elongation limits for different observatories, 3I-ATLAS is invisible to us. And this is not a random occurrence. This is not bad luck. This is built into the orbit, determined by the trajectory and timing of arrival. When you look up at the sky today, if it is daytime where you are, the Sun is there, and behind it, hidden from view, moving toward its closest approach to that Sun, is an object that has violated multiple assumptions about what interstellar visitors should look like. An object that, depending on who you ask, is either a mildly unusual comet or something that should not exist at all. And we cannot see it. We cannot track it. We cannot monitor what happens next. What happens next is Perihelion, October 29th, 8 days from now. 3I-ATLAS will reach its minimum distance from the Sun, approximately 130 million miles, about 1.4 astronomical units. That is just inside the orbit of Mars. Not particularly close in absolute terms. The Sun will not melt it or tear it apart with tidal forces. But perihelion is important for other reasons. It is the point of maximum energy input. Sunlight intensity follows an inverse square law. At perihelion, 3I-ATLAS receives more solar energy per square meter than at any other point in its trajectory. If it is a comet, this is when outgassing should peak. If it is something else, this is when energy-intensive operations become feasible. Loeb has calculated that at perihelion, the Sun deposits 33 gigawatts of power onto the surface of 3I-ATLAS, assuming a 5-kilometer diameter, 33 gigawatts. For reference, a large nuclear power plant produces about 1 gigawatt. The entire surface of this object will be receiving the equivalent of 33 power plants worth of energy continuously. That energy has to go somewhere. For a comet, it sublimates ice. For something artificial, it could charge batteries, run systems, power instruments, do whatever the design calls for. But perihelion is also important for another reason. The Oberth effect. This is a consequence of orbital mechanics that every spacecraft designer knows intimately. If you want to change your velocity, the most efficient place to do it is deep in a gravity well, at the point where you are moving fastest. A small thrust applied at high velocity produces a larger change in orbital energy than the same thrust applied at low velocity. The math works out such that burning fuel at perihelion gives you more bang for your buck than burning the same fuel farther out. This is why planetary flyby missions use gravity assists at closest approach. This is why Apollo missions did their major burns near the Moon or Earth. This is why any mission designed to maximize efficiency would time its propulsive maneuvers for perihelion. If 3I-ATLAS wanted to change course, if it had any capability to do so, now would be the time, 8 days from now, at the moment of closest approach, when it is moving fastest through the Sun's gravity well, when a velocity change of a few kilometers per second could redirect it toward a specific target. And we will not be watching. The object will be behind the Sun. We will not see the maneuver if it happens. We will not detect the thrust. We will only know after the fact when 3I-ATLAS emerges in November and we recalculate its trajectory. If the new path matches the old gravitational prediction, nothing unusual occurred. If it does not match, if there is any deviation that cannot be explained by outgassing or other natural forces, then something happened while we were blind. This is not paranoid speculation. This is simple orbital mechanics combined with the uncomfortable realization that our observation window has closed at the most critical moment. It is as if someone planned it this way, as if the arrival time and trajectory were calculated to place 3I-ATLAS behind the Sun during perihelion, maximizing its options while minimizing our ability to respond or even observe. That sounds like conspiracy thinking, but it is also just geometry. The orbit is what it is, the timing is what it is, and the consequences are unavoidable. Halloween is October 31st, 2 days after perihelion. Loeb mentioned this in one of his essays, the date chosen with a bit of dark humour. If 3I-ATLAS were going to reveal itself as something other than a comet, If it were going to deploy probes or change trajectory or transmit a signal, doing so around Halloween would be cosmically appropriate. A trick or treat from the stars. Spooky timing for a spooky possibility. Of course, the universe does not care about human holidays. October 31st is just another day in the calendar, but the proximity to perihelion makes it part of the critical window. Late October through early November is when anything unusual would happen, when we would start to see evidence of maneuvers or fragmentation or activity that does not fit the comet model. The fragmentation question is important. Natural comets sometimes break apart as they approach the Sun. The nucleus is a loose rubble pile held together by weak ice. Thermal stress from uneven heating creates cracks. Rotation generates centrifugal forces. Outgassing produces thrust that varies across the surface. All of these factors can combine to pull a comet apart. When it happens, you see multiple objects where there was one, each following a slightly different trajectory as they drift apart over days and weeks. If 3I-ATLAS fragments naturally, the pieces will separate with velocities of meters per second, maybe tens of meters per second. They will drift apart slowly, remaining loosely clustered for a long time. Their trajectories will be similar, diverging gradually due to small velocity differences. If you watch them over weeks, they will spread into a string of debris following nearly parallel paths. This is well understood. We've seen it happen to multiple comets. But if 3I-ATLAS is not fragmenting naturally, if it is releasing objects deliberately, the pattern would look different. The released objects would have higher separation velocities, hundreds of meters per second or more. They would diverge rapidly, each heading toward a different destination. After a few weeks, they would be scattered across the inner solar system, not clustered together, and their trajectories would not be parallel. They would point towards specific targets: Mars, Earth, Venus, Jupiter, each object on a calculated intercept course. Telling these scenarios apart requires observation. You need to track the fragments, measure their velocities, calculate their trajectories, and see if they are diverging randomly or converging on specific targets. This is doable, but it takes time. You need multiple observations over weeks to get accurate velocity vectors. By the time you have enough data to distinguish deliberate targeting from natural breakup, the objects could already be close to their targets. And if one of those targets is Earth, we would have very little time to react. Loeb has proposed that mini-probes ejected at perihelion with velocities of 30 to 40 kilometers per second could reach Earth in 60 to 70 days. That timeline puts them arriving late December, early January. Sarita's Christmas Day prediction, December 25th, falls right in the middle of that window. Different reasoning, same conclusion. Late December is when something might happen, when we might see secondary objects approaching Earth if the probe hypothesis has any validity. This is the scenario that keeps people awake at night. Not because it is likely. Base rates say this is almost certainly a natural comet doing weird but ultimately explainable things, but because if it is not natural, if there is even a small chance that 3I-ATLAS is artificial, then the implications cascade into territory we are not prepared to handle. We have no defense against hypersonic objects from space. We have no protocol for responding to intelligent contact initiated by something arriving unannounced at relativistic speeds. We have barely begun to think seriously about these possibilities, and now we might be facing them in real time. The black swan concept applies here. A black swan event is something with three characteristics. First, it is an outlier, lying outside the realm of regular expectations. Second, it carries extreme impact. Third, despite being an outlier, we concoct explanations for it after the fact, making it seem explainable and predictable in hindsight. Nassim Taleb wrote about this in Finance and History, but the concept applies anywhere. Most of history is shaped by low probability, high-impact events that nobody saw coming. 3I-ATLAS, if it turns out to be artificial, would be the ultimate black swan. We were not looking for it. We did not predict it. Our model said interstellar objects should be rare, small, and unremarkable. Then we found 3 in 8 years. The third one massive and weird. And now we're scrambling to figure out if the weirdness is natural or deliberate, with the answer determining whether this is a scientific curiosity or an existential event that redefines humanity's place in the cosmos. Loeb has briefed policymakers. He has written to the United Nations. He has appeared on news programs and published essays explaining the anomalies and urging caution. Not panic, but caution. We should be watching closely. We should be coordinating observations. We should be ready to mobilize assets if needed. The response so far has been muted. Most scientists remain skeptical. Most officials assume this will blow over, another false alarm in a long history of misidentified phenomena and overblown speculation. Maybe they're right. Probably they are right. But probably is not the same as certainly. And when you're dealing with possibilities that could reshape civilization, probably is not a comfortable margin. If there is a 1% chance 3I-ATLAS is artificial, that 1% demands serious attention. If there is even a 0.1% chance, it still demands attention. Because the downside of being wrong, of dismissing the possibility and being caught unprepared, is catastrophic. The downside of taking it seriously and being wrong is some wasted resources and mild embarrassment. The asymmetry is stark. Right now, today, as you listen to this, the critical moment is unfolding. 3I-ATLAS is behind the Sun, receiving maximum energy, at the optimal point for any maneuver or operation it might undertake. We cannot see it. We cannot stop it. We cannot even monitor what is happening. All we can do is wait. Wait for it to emerge. Wait for November observations. Wait to see if the trajectory has changed. Wait to see if fragments appear. Wait to see if December brings anything unexpected. The waiting is the hardest part. The not knowing. The realization that we're flying blind during the most important observation window we have had. The government shutdown did not help. The delayed high-res images did not help. The selective media briefings characterizing 3I-ATLAS as normal without evidence did not help. We are left with uncertainty at the exact moment when clarity is most needed, and uncertainty, when combined with stakes this high, becomes almost unbearable. 8 days to Perihelion, then the waiting game begins in earnest. November will tell us if the trajectory holds, December will tell us if anything approaches Earth. March 2026, when Juno observes 3I-ATLAS near Jupiter, will give us more data. But the critical moment is now. The moment we cannot see, the moment we cannot control. The moment that will determine whether this was all an academic exercise in unlikely astronomy or the beginning of something that changes everything. The Anomaly scorecard, Avi Loeb's rank 4. Avi Loeb developed a ranking system for interstellar objects. 0 means definitely natural, nothing unusual, just a rock or comet passing through. 10 means definitely artificial, unambiguous evidence of technology. No natural explanation possible. Most objects would score 0. Few might score 1 or 2 if they show minor oddities. 3I-ATLAS scores 4. That is high. That is high enough to demand serious investigation. And the score comes from stacking 8 distinct anomalies, each individually unusual, collectively unprecedented. We have covered several already. The trajectory alignment less than 1% probability, the sunward jet pointing toward the sun, the nickel emissions without iron, the massive size at least 5 kilometers. These are 4 of the 8. Now let us look at the others, the ones that complete the picture and push this object from merely unusual into genuinely anomalous territory. Anomaly 5 is extreme negative polarization. When light scatters off particles, it becomes polarized. The degree and direction of polarization tell you about the particle size, shape, and composition. Cometary dust typically produces positive polarization. Light scattered from the dust becomes partially polarized perpendicular to the scattering plane. This is well understood, well measured, consistent across all known comets. 3I-ATLAS shows negative polarization. The light is polarized parallel to the scattering plane. This is not just unusual, it is unprecedented. No known solar system comet shows this behavior. 2I Borisov did not show it. The polarization signature of 3I-ATLAS is, according to published observations, extreme and unexplained. What could cause negative polarization? Very specific particle properties. Either the particles are extremely small, much smaller than the wavelength of light, or they have unusual compositions, or the scattering geometry is different from what we expect. None of these explanations work well. If the particles were extremely small, they would not scatter much light. The coma would be dimmer. If the composition were unusual, it would have to be unusual in ways we've never seen in any dust sample from any solar system body. If the geometry were different, it would require a non-standard dust distribution that somehow produces this effect consistently across multiple observations. The polarization measurements come from professional observatories using standard techniques. This is not ambiguous data. The signal is clear. 3I-ATLAS exhibits negative polarization where positive is expected. That signature is documented, and it has no satisfying natural explanation yet. You can propose mechanisms, yes, but none of them fit cleanly. Each requires special circumstances, unusual conditions, rare configurations. And when you need rare configurations to explain multiple independent anomalies, you start to wonder if rare is the right word or if something else is happening. Anomaly 6 is water content, or rather the lack of it. Comets are supposed to be dirty snowballs, mixtures of water ice, carbon dioxide ice, and various other frozen volatiles embedded in rocky dust. Water is the primary component in most solar system comets. When they approach the Sun, water sublimes, creating the characteristic Comet and tail. Water dominates the spectroscopic signatures. Carbon dioxide is present, but usually in smaller amounts. 3I-ATLAS flips this ratio. Webb telescope data shows the gas plume is dominated by carbon dioxide with only about 4% water by mass. 4%. Most comets show the reverse, lots of water, some carbon dioxide. 2I Borisov was water-rich like a normal comet. 3I-ATLAS is carbon dioxide-rich to a degree that is extremely unusual. Why would an interstellar comet have so little water? One possibility is formation location. If 3I-ATLAS formed in the outer regions of its parent star system, very far from the star, temperatures would be cold enough that water ice is stable but carbon dioxide is not. Carbon dioxide would condense onto grains, water would stay locked in the solids. When the object was ejected and spent billions of years in interstellar space, cosmic ray bombardment could strip hydrogen from the surface, converting water ice to carbon dioxide through radiolysis. By the time it reaches our solar system, the surface layers are carbon dioxide rich. This explanation works in principle, but it requires the object to have spent a very long time in interstellar space, much longer than typical ejection timescales predict. It also requires very specific radiation processing that affects water more than carbon dioxide, which is chemically tricky. And it does not explain why the carbon dioxide to water ratio is so extreme. 4% water is not just low, it is a complete inversion of the typical comet composition. You would need to remove almost all the water or add enormous amounts of carbon dioxide, and neither process is easy to justify with known chemistry. Anomaly 7 is cyanide concentration. Cyanide, specifically cyanogen molecules, are common in comets. They form from organic compounds in the nucleus that break apart under ultraviolet radiation. The amount of cyanide relative to other emissions tells you about the organic chemistry of the comet. 3I-ATLAS shows cyanide emissions that are, as noted earlier, orders of magnitude stronger relative to water than typical comets. The nickel to cyanide ratio is also orders of magnitude higher than any known comet. These ratios are not slightly off, they're dramatically off. They place 3I-ATLAS in a chemical space occupied by no other observed object. Cyanide is interesting because it is a biomarker precursor. It is involved in prebiotic chemistry, in the formation of amino acids and nucleotides. High cyanide concentrations suggest organic-rich material, but organic-rich material typically comes with high water content, because the chemistry that produces organics also produces water. 3I-ATLAS has lots of organics, indicated by the cyanide, but almost no water. That is backwards. It is like finding a forest with no rain, a desert full of life. The combination does not fit the known pathways for planetary chemistry. Anomaly 8 is rotation period, and its relationship to golden ratio mathematics. This is where we veer into territory that most scientists will dismiss immediately. Sarita's calculations about the rotation period, matching Methuselah's age, about the golden ratio squared appearing in orbital relationships, about Fibonacci sequences encoded in the object's properties. These are the kind of numerological connections that make mainstream astronomers roll their eyes. And maybe rightly so. Humans are pattern seekers. We find meaning in noise. We see faces in clouds and hear messages in static. The brain is wired to detect patterns even when no patterns exist. But here is the thing. The rotation period is measured. 16.16 hours, plus or minus 0.01 hours. That is not made up. That is observational data. Converting to minutes gives 969.6. The similarity to 969, the biblical age of Methuselah, is coincidental unless you believe in divine encoding. But the mathematical relationship Sarita derives, the golden ratio squared, the Fibonacci connections to planetary orbits, those are mathematical facts if his arithmetic is correct. You can check the calculations. You can verify whether dividing 969.6 by Earth's sidereal period gives a result close to the golden ratio squared. If it does, that is a measurable relationship, not speculation. Does this relationship mean anything? Almost certainly not. The universe is full of numbers. If you look hard enough, you'll find golden ratios and Fibonacci sequences everywhere because those patterns are common in natural systems. Finding them in 3I-ATLAS proves nothing about intent or design. It is like finding the number pi in random data. If you look at enough random numbers, pi will appear eventually, but the appearance does not mean the data encodes pi deliberately. Still, Sarita's observations about the Fibonacci pulses on October 13th, if genuine, are harder to dismiss. A repeating pattern of 5, 8, 13 is specific. It is not just finding a ratio that happens to match some mathematical constant. It is observing discrete events in a sequence that matches a well-known series. If that observation is real, if it can be verified, it demands explanation. If it cannot be verified, if no other observatory saw these pulses, then it is likely instrumental error or misinterpretation. But Sarita claims the data exists. Until someone checks independently, we cannot rule it out entirely. These 8 anomalies, taken together, form the basis for Loeb's rank 4 assessment. Each anomaly individually might be explainable, unusual, rare, requiring specific conditions, but not impossible. The trajectory alignment, okay, low probability but not zero. The sunward jet, weird geometry and composition but natural mechanisms exist. The nickel without iron, puzzling but maybe some unknown chemistry. The massive size, statistically unlikely but large objects do get ejected occasionally. The negative polarization, unprecedented but scattering is complex. The water depletion, extreme but radiation processing could do this over time. The cyanide ratios off the charts but organic chemistry is complicated. The rotation period coincidences, numerology unless proven otherwise. Each anomaly gets a pass if you're generous with your assumptions, but all 8 together? That is a lot of generosity. That is a lot of assuming that multiple low probability features just happen to occur in the same object by chance. At some point, the stack of coincidences becomes heavy enough that you have to ask whether you are explaining the data or explaining it away, whether you are doing science or doing apologetics for a predetermined conclusion. Loeb is careful to say he does not know what 3I-ATLAS is. He is not claiming it is a spacecraft. He is not claiming aliens. He is saying the data is anomalous enough to warrant serious investigation without dismissing unconventional possibilities out of hand. A rank 4 means this object could be natural with unusual characteristics, or it could be something else. The data does not force a conclusion either way. It sits in the ambiguous middle, strange enough to be interesting, not strange enough to be definitive. The comparison to Oumuamua is instructive. Oumuamua also had anomalies, elongated shape, unusual light curve, non-gravitational acceleration that was hard to explain. Loeb argued it might be a light sail, a thin sheet accelerated by solar radiation pressure. Most astronomers argued it was a comet with unusual outgassing. The debate raged for years. Eventually, more detailed modelling showed that outgassing from specific vent configurations could explain the acceleration without visible coma. The natural explanation won, though some still argue the case is not closed. 3I-ATLAS is heading down a similar path. Anomalies documented, natural explanations proposed, debate intensifying. Will it end the same way, with a satisfying natural model that explains everything? Maybe. But 3I-ATLAS has more anomalies than Oumuamua did. The chemical signatures, the mass, the trajectory, the timing, all of it piles on top of the geometric and physical oddities. Explaining 3I-ATLAS naturally requires more special pleading, more unlikely coincidences, more just-so stories, and that makes the natural explanation less satisfying, even if it remains the most likely answer. November-December watch, the Emergence. Early November 2025. 3I-ATLAS will emerge from behind the Sun. After weeks of invisibility, after passing through Perihelion unseen, the object will move far enough from the Sun's glare that ground-based telescopes can reacquire it. This is when we get our first look at what happened during the hidden period. This is when we find out if anything changed. The first observations will focus on position. Where is 3I-ATLAS right now compared to where gravity predicts it should be? Orbital mechanics are deterministic. Given an object's position, velocity, and the gravitational forces acting on it, you can calculate its future position with high precision. Before 3I-ATLAS went behind the Sun, we knew its orbit. We measured its position repeatedly over months. Those measurements constrain the trajectory. When the object reappears, we will measure it again. If the new positions match the gravitational predictions, nothing unusual occurred. The object coasted through Perihelion following Newton's laws, no surprises. If the positions do not match, if there's any discrepancy beyond measurement error, that indicates a force acted on the object during the hidden period. Non-gravitational forces from outgassing can produce this. We discussed earlier that 3I-ATLAS has shown no detectable non-gravitational acceleration through September, implying enormous mass. But conditions at Perihelion are different. The object is much closer to the Sun. Solar heating is more intense. Outgassing should peak. Even a massive object might show detectable acceleration if the outgassing is strong enough and asymmetric enough. So finding a trajectory change in November would not immediately prove anything artificial. It would just tell us that forces beyond gravity are at play. But the nature of the trajectory change would matter. If 3I-ATLAS has drifted slightly off course in a random direction, that looks like outgassing. Comets vent from multiple locations. The thrust vector changes as the nucleus rotates. The net result is a small, somewhat unpredictable acceleration that averages out over time. If the object has shifted in a specific direction, if the new trajectory points toward a particular target, that looks different. That looks like a course correction. Distinguishing these scenarios requires careful analysis of the velocity change vector. Is it consistent with random outgassing, or does it show evidence of deliberate targeting? This analysis will take time. Weeks, possibly months. You need multiple position measurements to determine velocity accurately. You need to model the expected outgassing forces based on the surface temperature distribution and rotation state. You need to compare the observed acceleration to the model predictions. Only then can you say whether what you're seeing is natural or anomalous. By the time the analysis is complete, we will be well into December, approaching the timeline that both Sarita and Loeb have pointed to as potentially significant. November 4th, 2025. ESA's JUICE spacecraft will pass within 64 million kilometers of 3I-ATLAS. JUICE, the Jupiter Icy Moons Explorer, is en route to Jupiter, where it will study Europa, Ganymede, and Callisto. But its trajectory happens to bring it relatively close to 3I-ATLAS in early November, just days after Perihelion. The spacecraft carries a suite of instruments, including cameras, spectrometers, and magnetometers. It will observe 3I-ATLAS from a distance, capturing data that complements ground-based observations. JUICE will see 3I-ATLAS from a different angle than Earth-based telescopes. It will be positioned elsewhere in the solar system, providing a second viewpoint for triangulation. If 3I-ATLAS is fragmented, if multiple objects now exist where there was one, JUICE might be able to resolve them as separate sources. If the object shows unusual activity, jets, flares, anything beyond normal cometary behavior, JUICE's instruments should detect it. The data will take time to downlink and process, but by mid-November we should have a preliminary report from the JUICE team, describing what they saw. This is important because JUICE is an active mission with full operational support. Unlike NASA during the shutdown, ESA has been forthcoming with data releases. If JUICE observes something truly anomalous, we will likely hear about it relatively quickly. And if JUICE sees nothing unusual, if 3I-ATLAS appears to be behaving like a normal comet from the spacecraft's perspective, that would be reassuring. Not conclusive, but reassuring. December 19th, 2025. 3I-ATLAS reaches its closest approach to Earth, 269 million kilometers, about 1.8 astronomical units. This is not particularly close. The object will be farther from Earth than Mars is at its nearest, but it is close enough for detailed observation. Large ground-based telescopes, space telescopes, amateur astronomers with good equipment, all will be able to track the object. The viewing geometry will be favourable. 3I-ATLAS will be well placed in the sky, visible for extended periods, allowing multiple observations per night. This is when we should see the object at its best. If the nucleus is large, if it reflects enough light, we might get size estimates from photometry alone. If it is still outgassing, spectroscopy will reveal the composition of the plume. If it has fragmented, we will see multiple objects spread along the orbit. If it has released anything, mini-probes, debris, whatever, those objects will have had 2 months to separate from the main body. By December, they should be far enough apart to resolve individually if they're bright enough, and if anyone is looking carefully. Sarita's timeline points to December the 25th, Christmas Day. He claims this is when 3I-ATLAS will reach the Great Pyramid angle relative to Earth. The geometry is calculable. If you know the positions of 3I-ATLAS and Earth on December 25th, you can compute the angle between them as seen from a reference point. Whether that angle matches the slope of the Great Pyramid is a matter of arithmetic. Sarita could be right or wrong, but the claim is testable. On December 25th, someone with orbital calculation tools can check. If the angle matches, that is an interesting coincidence. If it does not match, Sarita's prediction fails, and the entire Fibonacci message interpretation becomes less credible. But even if the pyramid angle prediction is wrong, the date remains significant because of the Oberth maneuver timeline. Objects released from 3I-ATLAS at Perihelion, October 29th, would take roughly 60 days to reach Earth if given an initial velocity of 30 to 40 kilometers per second. 60 days from October 29th is late December. Christmas Day falls well within that arrival window, so even without Sarita's esoteric geometry, December 25th is a date worth watching simply because the physics puts it in the arrival corridor for any hypothetical probes. What would we see if probes arrived? That depends on their size and activity. If they are small, meter-scale objects, and inactive, we would not see them until they were very close, maybe inside the moon's orbit. Detecting dark objects at interplanetary distances is hard. They reflect almost no light. They blend into the background. Only if they are actively emitting, radiating heat, transmitting signals, firing engines, would they show up at long range. If they are larger, tens of meters, they might be detectable by reflected sunlight once they get within a few million kilometers of Earth. Our asteroid detection systems would have a chance of spotting them. But here is the uncomfortable part. If something is approaching Earth deliberately, if it has trajectory control, it could maneuver to avoid detection. It could adjust its path to stay in the sun's glare, backlit and invisible. It could time its approach to coincide with a new moon when the sky is darkest and optical surveys are least effective. It could use a minimum energy trajectory that keeps velocity low until the final approach, making it harder to distinguish from natural debris. If something wanted to reach Earth undetected, it could probably do so with modest technology. Our detection grid is not that good. We miss asteroids all the time. We would miss a probe if it tried to stay hidden. This is not paranoia. This is just acknowledging the limitations of our observational infrastructure. We do not have comprehensive space situational awareness. We do not track every object in cislunar space. We focus on known threats, catalogued satellites, large debris. Small uncatalogued objects slip through. Something arriving from deep space, on an unusual trajectory, without prior warning, would be hard to track until it was very close. And very close, at interplanetary speeds, gives very little reaction time. If nothing arrives by early January, if December passes without incident, the probe hypothesis dies. It becomes clear that 3I-ATLAS was just a comet, however unusual, and all the speculation was unfounded. Life goes on. Science adjusts its models slightly to accommodate the odd chemical signatures and moves forward. The narrative shifts to lessons learned about not jumping to conclusions, about the importance of patience and rigor, about how even smart people can get caught up in patterns that are not real. But if something does arrive, if anything appears in cislunar space between late December and early January that was not there before, that cannot be explained as natural debris or known spacecraft, then everything changes. The questions escalate instantly. What is it? Where did it come from? What does it want? Is it communicating? Is it hostile? Is it just observing? Every space agency, every government, every military would mobilize. The detection would be classified immediately, analyzed in secure facilities, briefed to heads of state before any public announcement. And by the time the public learned anything, decisions would already be made. This is the scenario that hangs over the next few months. Low probability, high impact. Almost certainly nothing will happen. Almost certainly 3I-ATLAS is natural. Almost certainly we will look back on this period and laugh at how worked up we got over a weird comet. But almost certainly is not the same as certainly, and the gap between almost and absolute is where the interesting possibilities live. March 16th, 2026. 3I-ATLAS will pass within 54 million kilometers of Jupiter. The Juno spacecraft orbits Jupiter, studying its atmosphere, magnetic field, and radiation environment. Juno's trajectory happens to position it favorably for observing 3I-ATLAS during this close approach. The spacecraft carries instruments that can detect radio emissions, ultraviolet light, infrared heat, and magnetic fields. If 3I-ATLAS is emitting anything beyond reflected sunlight and thermal radiation, Juno should detect it. Loeb has recommended that Juno attempt to observe 3I-ATLAS. He published a paper with Adam Hibbard and Adam Crowell outlining the scientific value of such observations. Reppers Anomaly and Luna endorsed the recommendation in a letter to NASA. The idea is to use Juno's unique position near Jupiter to gather data that complements Earth-based observations. Juno sees 3I-ATLAS from a different angle, through different instruments, at a time when the object is farther from the Sun and has cooled somewhat. The UV and radio observations are particularly interesting. If 3I-ATLAS were transmitting signals, if it were using electromagnetic communication, Juno might detect it. Radio waves travel at the speed of light. They're not attenuated much by distance. A transmission from 3I-ATLAS near Jupiter would reach Juno in minutes. If the spacecraft's radio instrument happens to be listening at the right frequency, it would pick up the signal. This is unlikely. Radio spectrum is vast. Finding a signal without knowing the frequency is like searching for a specific grain of sand on a beach. But if a signal is being transmitted at high power, if it is meant to be noticed, Juno might stumble across it. The infrared observations would show the temperature distribution on 3I-ATLAS. If the object is a comet, the sunward side should be warmer, the night side cooler, with a gradient determined by rotation and thermal inertia. If the object has internal heat sources, power systems, active machinery, the thermal signature might look different. Hotspots in unexpected locations, stable temperature anomalies that do not correlate with solar illumination. These signatures would be subtle, but detectable if you know what to look for. So the observation timeline stretches from November 2025 through March 2026. 5 months of watching, 5 months of data collection, 5 months to determine if 3I-ATLAS is what it appears to be or something else entirely. And through all of it, the nagging awareness that we are operating on incomplete information. We still do not have the high-rise images, we still do not know the true size, we still do not have definitive explanations for the chemical anomalies. We are watching something we do not fully understand, trying to predict what it will do next, hoping we recognize the signs if something unusual happens. The emergence in November will tell us if the trajectory changed, December will tell us if anything approaches Earth, March will give us Juno data. By next spring, we should have enough information to close the book on 3I-ATLAS. To say definitively whether this was a fascinating but natural comet or the beginning of something much larger. Until then, we watch. We wait. We hope that watching is enough. The human response, are we ready? In August 2025, Avi Loeb addressed the United Nations. Not in person, not standing at a podium before the General Assembly, but in writing through formal communications with scientific advisory bodies that feed into policy discussions. The message was measured, careful, not alarmist, but not dismissive either. 3I-ATLAS exhibits anomalies that warrant attention. We should coordinate international observations. We should prepare for the possibility, however remote, that this object represents something unprecedented. We should not panic, but we should not ignore it either. The response from the UN was polite. Thank you for bringing this to our attention. We will monitor the situation. Standard bureaucratic language that commits to nothing while acknowledging receipt of information. No emergency sessions, no special committees formed, no global coordination initiative launched. Just acknowledgement and filing away. Business as usual. Loeb also briefed members of Congress. Rep. Anapolina Luna has been vocal about 3I-ATLAS, asking questions publicly, requesting information from NASA, endorsing observation proposals. Other members have expressed interest privately but remained quiet publicly, perhaps wary of being associated with speculation about alien visitors. The political calculation is obvious. If 3I-ATLAS turns out to be a comet, Anyone who raised alarms looks foolish. Better to wait for definitive evidence before making public statements that could be used against you later. This caution is understandable, but frustrating. Preparing for a low probability high impact event requires acting before you have definitive evidence. If you wait for certainty, you wait too long. By the time you know for sure that something unusual is happening, your window to respond has closed. This is the core tension in risk management. You cannot prepare for everything. Resources are limited. Attention is limited. You have to choose which risks to take seriously, and choosing requires making judgments under uncertainty. Loeb argues that the risks associated with ignoring 3I-ATLAS outweigh the costs of taking it seriously. If we monitor closely, coordinate observations, develop response plans, and nothing happens, we waste some telescope time and planning effort. Not ideal, but manageable. If we ignore it, assume it is natural, and then discover in December or January that something is approaching Earth, we have no time to respond. We are caught flat-footed. The asymmetry favours caution, favours preparation, favours treating this as a potential black swan event until proven otherwise. But institutions do not think in terms of black swans. They think in terms of base rates and precedent. How many times have we thought something unusual was happening and it turned out to be mundane? Hundreds of times. Thousands. Every UFO sighting that turned out to be a weather balloon. Every anomalous signal that turned out to be instrumental noise. Every weird astronomical phenomenon that turned out to have a conventional explanation. The track record of unusual equals alien is abysmal. So when someone says this time might be different, the institutional response is skepticism. Show us proof. Show us something definitive. Until then, we assume natural. This is rational given the history, but it is also dangerous if applied too rigidly. Black swans, by definition, are events outside normal experience. They do not fit the pattern. Judging them by past base rates misses the point. The fact that all previous anomalies were natural does not guarantee that the next one will be. Each event should be evaluated on its own merits, not prejudged based on aggregate statistics. 3I-ATLAS, evaluated on its own merits, exhibits 8 documented anomalies. Each has proposed natural explanations. None of those explanations are fully satisfying. Together, the anomalies paint a picture of something that does not quite fit our understanding. Maybe we expand our understanding. Maybe we're missing some subtle physics or chemistry. Or maybe, just maybe, we're seeing something genuinely new. The question is, how do we respond to that uncertainty? Loeb has proposed several concrete steps. First, maintain continuous observation of 3I-ATLAS from multiple observatories. Do not let it out of sight once it emerges in November. Track it carefully. Measure everything. Position, velocity, brightness, spectrum, polarization, everything. Build a comprehensive dataset that allows detailed analysis. Second, coordinate internationally. Share data in real time. Do not hoard observations behind national or institutional barriers. This is too important for petty competition. If something unusual is happening, everyone needs to know as soon as possible. Establish secure channels for rapid communication between observatories and space agencies. Agree on protocols for what constitutes an alert-level event. Third, prepare contingency plans. What do we do if the trajectory changes in November? What do we do if fragments appear? What do we do if something approaches Earth in December? These questions need answers before the events occur. Gaming out scenarios, identifying decision points, clarifying chains of command, all of this takes time. If you wait until the crisis is underway, you improvise badly. Fourth, fund observation infrastructure. We need better sky surveys, better tracking of objects in cislunar space, better sensors that can detect small objects at interplanetary distances. The Rubin Observatory is coming online, which will help. But we also need Northern Hemisphere coverage. Loeb has suggested funding a northern equivalent to Rubin, a large survey telescope that can scan the northern sky nightly looking for moving objects. The cost would be comparable to a single military aircraft. The benefit, in terms of asteroid detection and space situational awareness, would be enormous. Fifth, and this is the controversial one, take the artificial hypothesis seriously. Do not dismiss it out of hand. Investigate it rigorously. Model what an artificial object would look like, how it would behave, what signatures it would produce. Then compare those predictions to the observations. If the artificial model fits the data better than the natural model, that is important information. If the natural model fits better, that is also important, but you cannot make the comparison if you refuse to build the artificial model in the first place. This last point is where Loeb faces the most pushback. Scientists accuse him of sensationalism, of chasing headlines, of damaging the credibility of astronomy by lending legitimacy to fringe speculation. Loeb counters that refusing to consider unconventional hypotheses is not science, it is dogma. Science is supposed to be open-minded, willing to follow evidence even into uncomfortable territory. The stigma around discussing artificial origins for anomalous objects is a cultural problem, not a scientific one. The cultural problem runs deep. For decades, any discussion of extraterrestrial intelligence in the context of observed phenomena has been career poison. Scientists who take UFOs seriously, or who suggest that ambiguous data might indicate technology, get ostracized. Funding dries up, colleagues distance themselves, tenure becomes harder to achieve. The incentive structure pushes researchers toward conventional explanations, even when those explanations require tortured logic. This creates a blind spot. If an actual artificial object entered the solar system, how would we recognize it? What signatures would we look for? We have not thought seriously about these questions because thinking about them carries professional risk. So when something like 3I-ATLAS appears, we have no framework for evaluating it except by trying to fit it into the natural category. And when it does not fit cleanly, we invent new natural subcategories rather than considering the alternative. Loeb argues this needs to change. We need a scientific framework for evaluating potential technosignatures in observational data. We need researchers working on this without fear of ruining their careers. We need funding for instruments designed to detect artificial objects, not just natural ones. And we need a cultural shift that treats the search for evidence of extraterrestrial technology as legitimate science rather than fringe speculation. The Galileo project, which Loeb directs, is attempting to do this. The project has deployed observatories that scan the sky for unidentified aerial phenomena, UAPs, using multiple sensors to gather high-quality data. The goal is not to prove aliens exist. The goal is to gather data good enough to distinguish natural phenomena, human technology, and potentially non-human technology. If most UAPs turn out to be drones, balloons, and optical illusions, great. That is useful information. If some turn out to be something else, that is also useful information. The project has limited funding and operates on a shoestring compared to traditional astronomy programs, but it represents a first step toward treating the search for extraterrestrial technology as a legitimate observational science. And if 3I-ATLAS turns out to be artificial, if the next few months bring evidence that cannot be explained naturally, the Galileo project and similar efforts will suddenly seem prescient rather than fringe. But what if 3I-ATLAS is artificial? What if, in December or January, something approaches Earth that we cannot explain? What then? The scenarios cascade rapidly into uncharted territory. First, confirmation. Multiple observatories would need to verify the object's existence and trajectory. You cannot declare first contact based on a single anomalous data point. Independent confirmation is essential. Second, characterization. What is it? How big? What is it made of? Is it transmitting? Is it maneuvering? You gather as much data as possible using every available instrument. Third, classification. Is it a probe, a derelict, a functioning spacecraft, an automated system? These distinctions matter. A probe suggests deliberate exploration, intelligence with intent. A derelict suggests past intelligence but no current threat. An active spacecraft suggests current intelligence and potential for interaction or conflict. Fourth, communication attempts. Do we try to signal it? Do we attempt contact? Or do we stay quiet and observe? The decision depends on the classification and on philosophical questions about whether revealing our presence is wise. This is where things get complicated. If 3I-ATLAS is a probe and it is heading for Earth, it already knows we are here. Attempting contact might be pointless, or might provoke a response we're not ready for. If it is automated, programmed for a specific mission, it might not respond to our signals. If it is controlled by intelligence elsewhere, response time could be years depending on the distance to the controlling entity. All of this assumes the object is willing and able to communicate with us, which is a huge assumption. The other possibility is defense. If something approaches Earth and we determine it as a threat, what do we do? We have no space defense infrastructure, we have some capability to intercept ballistic missiles, but those are moving at a few kilometers per second in predictable trajectories. An object from deep space would be moving at tens of kilometers per second on a trajectory we might not understand until it is too late. Intercepting it would require launching something to match trajectories, which takes time we might not have. Nuclear weapons could be used in theory. Launch a missile, detonate it near the object, try to deflect or destroy it, but nukes in space are problematic. They do not work the same way they do in atmosphere. No shockwave, just radiation and kinetic debris. You would need multiple warheads, carefully timed, to have any effect on a solid object. And if the object is large, as 3I-ATLAS appears to be, nukes might not do much. You would fragment it at best, creating multiple smaller threats instead of one large one. The honest answer is we are not ready. If something artificial is approaching Earth right now, we have no good options. We can observe, we can analyze, we can attempt communication, but we cannot effectively intercept, defend, or control the situation. We are passengers, watching events unfold, hoping that whatever is coming is benign or at least indifferent to us. That is an uncomfortable realization. That is a level of helplessness most people do not like to contemplate. Loeb has suggested that the discovery of extraterrestrial technology, even if it is just a derelict probe with no intelligent operators, would reset human priorities. We would stop fighting over borders and resources and ideologies if we realized we are not alone, that we are not the pinnacle of intelligence, that we are late arrivals to a cosmos already populated by others. The petty conflicts that dominate human history would seem trivial in comparison to the larger context. We would unite, out of necessity if not idealism, to face the implications together. This is optimistic. History suggests humans are good at finding reasons to fight even when external threats loom. But maybe, just maybe, the shock of confirmed contact would be enough to jar us out of our usual patterns. Maybe the realization that we are being visited, studied, evaluated by something with technology beyond ours would inspire cooperation rather than competition. Maybe we would rise to the occasion. Or maybe we would fracture. Different nations claiming different interpretations. Religious groups declaring it divine or demonic. Conspiracy theorists blaming governments for hiding the truth. Panic in the streets as people realize our assumptions about reality are wrong. Markets crashing as investors flee to safety. It could go very badly very quickly, and preventing that, managing the revelation in a way that minimizes chaos, requires preparation that we have not done. So we sit here, in October 2025, watching an object hide behind the sun, wondering what happens next, hoping it is nothing, preparing for the possibility that it is something, knowing that either way, the next few months will tell us whether we live in a universe where we are alone or one where we have neighbours, and if we have neighbours, whether those neighbours are friendly, hostile, or utterly indifferent to the small blue planet they are passing on their way to somewhere else.